We will now talk about the process of anti-differentiation, and in particular, its applications to the functions of position, velocity, and acceleration. We will start by watching a video by Felix Baumgartner trying to attempt to break the speed of sound in a free fall.
Release. I'm going over. Generate.
There are two interesting points in the video that I'd like to draw your attention to. First of all, it's pretty clearly visible that the Earth is in fact round, so I just want to clear up any misconceptions about the fact that it is an almost perfect sphere. And second, you notice that right after somebody declares Felix is stable, they start clapping, and that is before he lands, and that is because they were really worried about him actually going into a spin, because the amount of gravitational, like centrifugal forces might have caused him to black out, and he was the only person in charge of his own parachute. So that point in the video is where they were sure that he was actually going to make it back to Earth alive. Now, I wanted to show you the graphs of the altitude or the position and the speed or velocity of Felix's fall to discuss that different graphs can be useful for different kinds of information. So first of all, these graphs are derivatives of each other, right? So the altitude function is as computed, but the speed function is really the derivative of the position function. So here we have a graph and its derivative. The speed of sound, which he was trying to break, is anywhere between 330 and 340 meters per second, depending on the temperature of the air surrounding it. So 331, for example, here corresponds to 0 degrees Celsius, whereas 343 corresponds to about the room temperature of 23 degrees Celsius. So the natural question to ask really is, did he actually achieve the speed of sound in his fall? For that, we're going to look at the speed function. And here we can see that the highest point, or the max speed, occurs just above the 350 mark. So yes, we can be pretty certain that he did actually break the sound barrier. But what is really surprising about this graph is right after he manages to hit that peak speed, his speed decreases drastically. So what happened? We didn't notice that in the video, and he pulls his parachute way later. So why such a sudden drop in speed? Let's take a look at what we can figure out here. So this occurred just about at 50 seconds, or maybe just a little bit before, when he was going at the speed of just around 350 meters per second. Now, again, the speed doesn't tell us much, but let's see what that corresponds to on the altitude graph. And here, just before 50 seconds, is approximately 30,000 meters, or 30 kilometers. What happens about 30 kilometers above Earth is there is no atmosphere above that. The 30 kilometers is when you actually enter troposphere with oxygen. Oxygen is great for life because that's what we breathe, but it's not good for free-falling objects because it creates drag due to air resistance. So this, in fact, had to be accounted for when mathematicians had to figure out how high does the Felix's little capsule have to go up to so he can jump off of it, so he can reach the speed of sound without atmosphere surrounding him. Because in our atmosphere, he wouldn't be able to reach that as a maximum speed. So this highlights that things like altitude and speed and acceleration are extremely important in computations that surround any kind of space explorations. Let's now talk about a more general setup of uniform motion with constant acceleration, which occurs exactly in the process of dropping the ball, and the only force acting on that object being gravity. Now, instead of going through this myself, I'm going to let our textbook author, Leah Keshes, show you how to derive these things. In that, I also would like to draw your attention to the fact that the textbook for the course is a great resource that has all of the material that we're covering, except for several applications, but all of the theoretical background, lots of different types of examples, lots of different exercises, as well as links to different types of videos as well. So please check it out, and off to Leah we go.
Let's recall that if we go from a displacement to a velocity to an acceleration, this is the process of differentiation. If we go the other way, this is anti-differentiation. In fact, in the example we do now, we're going to start with information about the acceleration and deduce something about both the velocities and the displacement. So we're going to assume what's called uniformly accelerated motion, namely that the acceleration at any given time is constant, and in fact, we'll denote it as minus g, where g here stands for the acceleration due to gravity. In other words, we're going to be thinking of a ball that's falling under the force of gravity and accelerating at that uniform rate. The derivative of the velocity, which recall is the same as the acceleration, is equal to minus g. From that, we can deduce something about the velocity itself. Now, let's think for a minute. What sort of function did we have to start off with in order that when we differentiate it, we get minus g? Well, clearly it should be something of the form minus g times t, because of course when we differentiate this, we'll get simply this coefficient minus g. In fact, there could be any other additive constant because the derivative of that constant would vanish when we differentiate. Now, what does this constant mean? Let's look at the fact that if we plug in t equals 0, we get v of 0 equal to c, and so therefore c is actually denoting the initial velocity of the object. That initial velocity could be positive or negative. In our case, perhaps the ball is moving upwards. Let's see what happens as a result. Okay, now from the velocity, we can say something about the displacement. So let's recall, first of all, that the derivative of the displacement is the same as the velocity, and therefore we can say something about the displacement itself by finding a function whose derivative is this quantity. Now, in order to be able to get this, when we differentiate the displacement, we have to have one higher power for the variable. So when we differentiate t squared, we'll get the power t to the 1. But we'll also get a factor of 2 that comes out. To account for that, we're going to divide this by 2. And so altogether, we'll have minus g over 2 t squared, remembering that now this is v0. The second part, we'll need the function v0t in order to give us this. And finally, we may have another constant k that appears here, which again, when differentiated, vanishes to give us the velocity. About this constant, we could say the following. If we look at the displacement at time 0, these two terms vanish, and we're left with y at time 0 equals k. We're going to denote that by the quantity y0 for initial displacement. So altogether, we've been able to figure out both the velocity and the displacement.
So just to quickly recap, the process of going from the position to the velocity to the acceleration is differentiation. The process of going backwards is the acceleration. So we've seen in the video how Leah has derived all the formulas that you will likely see in a physics class, and how these are nothing but antiderivatives of each other in the process of simply applying a power and anti-power rule and making sure that you calculate the corresponding constants. Now for our next application, let's take a look at constant acceleration on the moon. There, we don't even have to talk about our simplified model of assuming no air resistance and therefore no drag, because there's no atmosphere on the moon. So our simplified model of assuming that the forces of gravity are the only forces acting upon an object are actually all of the assumptions that we need to make. So first, let's take a look at the video of how David Scott drops a feather and a hammer on the surface of the moon.
In my left hand, I have a feather. In my right hand, a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago, who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? Which proves that Mr. Galileo was correct in his findings.
Now, the reason that the astronaut points out that the feather is that of a falcon, and you will see an application of that in class, is that falcon is actually the fastest bird on Earth and the fastest in the free fall form. So they've managed to bring a feather up there just to run one of these experiments on the surface of the moon. Now, in all of the word problems, I strongly encourage you to, where possible, draw a little bit of a graphical illustration of what is going on. You don't need any artistic skills, and trust me, I don't have very many, but just producing a little picture will sometimes help you figure out exactly what is happening in the situation. So in this case, we have an astronaut who is dropping a feather and a hammer from about, we're told, 4 feet of height. Okay, we know the acceleration on the moon due to gravity, and we would like to figure out when does that object, when do either of those objects hit the actual surface of the moon. So as in the previous derivation, nothing has changed here except for the gravity constant is different, but we will start with the acceleration, which is minus 5.2, and we should move in to the velocity function, which we then know to be minus 5.2t plus the initial velocity. Now we saw that the astronaut was not throwing the objects onto the surface of the moon, but was rather just dropping them. So initial velocity in this case will be 0. We then take one more step back in anti-differentiation for displacement or position function. In this case, it's the height. And we can see that this is going to be 5.2 t squared over 2 plus, according to the most general formula, plus initial velocity and the time plus the initial height. Now, the initial velocity was 0, so this middle term is 0. But the initial height, as suggested by our little picture here, is 4 feet above ground. So my initial height will be 4 feet. So now overall, the height function is given by minus 5.2 t squared over 2 plus 4. And the question is asking, when does the object, either of the objects, when do they both hit the surface of the moon? Now the surface of the moon here is of course our ground 0. So the question becomes, when does this function equal to 0? So we need to solve for h of t being 0. Okay, and this is just a quadratic equation and a fairly straightforward one at that. So I encourage you to actually do these calculations by yourself. I should warn you though that for a quadratic equation, you should get 2 roots unless they're repeated. So here, in fact, we will get 2 roots and it will be plus minus 1.24, and the time was measured in seconds. Now notice that I'm getting a positive and the negative, and then of course we're speaking about time, so the negative root should be rejected. However, the positive one is the one that remains. And so the answer to our question, how long does it take for the objects to hit the surface, the ground, is 1.24 seconds.